In this lecture, we look at introduction to limits using a calculator. We may use a calculator to estimate a limit. In this case, it's convenient to create a table of x values that approach the target A and examine the y values that occur then. Let's use our calculator to guess the limit as x approaches 2 of this quotient. We're going to do this by coming up with some x values close to 2. We don't care about what happened at 2, but we want some x values close to 2. So we might create a table like this. Here we have x values like 2.1, 2.01, 2.001. Notice these x values are getting close to the 2, and my function output is 0.749 something. We might guess from this work that as x approaches 2 from above, that the function f of x is approaching 0.75. And so we would write this way. The limit as x approaches 2 from above is this expression. The plus sign above the 2 in the limit notation means that we are approaching 2 from above, from values higher than 2, from the right side on the x-axis. We could approach 2 using numbers slightly lower from the left side on the x-axis, so maybe we might make x be 1.9 or 1.99 or 1.999 or 1.9998376. Anyway, once again, the values of the function seem to be approaching 0.75. These are the y values that seem to be getting close to 0.75 as the x values rise up to 2 from below, and so we would write the limit as x approaches 2 from below of this fraction is 0.75. Here, the negative sign above the 2 that I've put in red means that we're trying out numbers slightly less than 2. Our calculator is suggesting that the limit as x approaches 2 from above is 0.75, and as x approaches 2 from below is 0.75. Since we're approaching 0.75 no matter which way we come at 2, then we summarize this by saying the limit of f of x as x approaches 2 is 0.75. We write it this way. Notice that there's no sign of direction over the 2. There's no plus or minus. We're not coming at 2 from just one side, but from both sides. So the limit as x approaches 2 of this fraction is 0.75. One might notice in this case that the value of 0.75 is not surprising. Although we've stressed that limits have nothing to do particularly with the value at a, in this case, if we just go ahead and plug in x equals 2, we find that f of 2 is 0.75. So it should not be too surprising that as x gets close to 2, my function gets close to 0.75. In this case, and maybe, possibly just in this case, we could have skipped computing values near x equals 2 and gone right to plugging in the value 2. But this is because the function f of x is continuous at x equals 2. We will say more about this later. Let's do another example using a calculator. Let's find the limit as t approaches 1 from below of this fraction. We create a table of values. We want t to come up to 1 from below, so we might try 0.9, 0.99, 0.999, and so on. And notice that the outputs, f of t, is numbers very close to 2. And they seem to be getting closer and closer to 2, so we might guess that the limit as t approaches 1 from below of this fraction is equal to 2. We agreed that as t approaches 1 from below, we got 2. We got this table. Notice this time that it does no good to try and skip past our limit computation and just plug in t equals 1. The function f of t is not defined at t equals 1 because the denominator is 0. So we couldn't plug in a 1 for t and get 2. That's not going to happen. This direct temp would fail here. We have to plug in some values near 1. Here's another problem, an important one for this class. Let's use our calculator to estimate the limit as theta approaches 0 of sine theta over theta. Notice, by the way, that if we plug in 0 to this expression, we'll get 0 over 0, which does not make any sense. But we want a limit. We're going to plug in theta values close to 0. Here are some values of sine theta over theta as theta approaches 0 from above. We're going to plug in some positive numbers like 0.1, 0.01, 0.001, and the theta values in the left-hand column are going down to 0, and the outputs in the right-hand column are approaching 1. So this suggests that the limit as theta approaches 0 from above is 1. By the way, if we're doing this, we must be using radians. We will not measure angles in degrees. We've discovered the limit as theta approaches 0 from above is 1. What about the limit as theta approaches 0 from below? In this case, since sine is an odd function, we really don't have to do the work. Sine's an odd function, so the sine of minus theta will be the negative of sine theta. And then since sine of theta is odd and theta is odd, sine of theta over theta is an even function. And so the values of sine of theta over theta when theta is negative will be exactly the same as when theta is positive. So the table we had in the previous slide, when we plug in negative values, ends up giving the same output. The column on the right is the same as before. In other words, the limit as theta approaches 0 from below is 1. And since the one-sided limits agree, the limit as theta approaches 0 from above is 1, the limit as theta approaches 0 from below of this fraction is 1, then the limit as theta approaches 0 from any direction of sine theta over theta is equal to 1. Playing with a calculator here suggests that the limit as theta approaches 0 from either direction of sine theta over theta is equal to 1. We will argue this result more rigorously later because it is an important one for this course. You might try this problem on your own with your own calculator values, but make sure your calculator is set to radians mode. It does not make sense really in calculus to work in degrees. The third way to look at limits is algebraically, using the concept of continuity. That will be the subject of the next section.